Alright guys, this is unit number 6, lesson number 7, and we will be using exponential models based on percent growth. And basically we're just going to see a lot of real world situations where percents come up. So let's just start right with example number 1, or exercise number 1. It says a population of fruit flies is growing at a constant rate of 6% per hour, meaning the population is increasing. If the population starts with 28 flies where t equals 0, which would be your time. So using what we've learned in the last couple lessons, determine the population after each of the following amounts of time. Show the calculations. So I'm just going to kind of fill this one out with you. So it started at 28 when t was 0, which is time. After 1 hour, what would happen? So what we would do is take that 28 and multiply it by 1.06, because remember 6% would be 0.06. And it's increasing, so we have to use the 106%. So we're taking the 100% of 28 and adding another 6% onto it, which is 1.06. So you just multiply that out, and you get roughly 30 flies. So it went up to 2. Hour 2, basically, remember, we'd take this answer, this 29.68, and we would do the exact same thing to it. Now remember, this 29.68 really came from this. Hopefully this makes sense to you. So notice this was 28 times 0.106. Now we're multiplying it by another 0.106. So really what we're doing is doing 28 times 0.06 twice, or to the second power, which notice is matching our hours. And then we would multiply that out, roughly get 31 flies. Alright, so we'll just continue with that. And then so again we would take this amount here and multiply it by the 0.106. And remember, this one is equal to 2 of them. So if we're going to multiply it by 1 more, really we're taking that initial 28 and multiplying it by 3 sets of 0.106. There we go. So hopefully with this pattern you can see it's just like our exponential functions that we've been doing. This is our initial amount, this is our growth rate, and then our exponential is how many times we're doing that. So you should easily be able to set up now a function. Notice it wants you to use p and t. So see if you can write that now in the form of a function notation like that. Alright, how'd you do? Did you write something like that? So P of t, so population, when you put in the time, there's your initial amount, there's your growth rate, and there's your exponent of time. So it should be pretty easy now to find what the value of P of 24. So go ahead and do that now. Okay, how'd you do? Hopefully you ended up with about 113. So you could see they just rounded to 113. Pretty easy work to do. Alright, let's keep moving on. Okay, so it says, what does your calculation you made in part C represent about the fly population? State the range of the population function over the domain of when t is 0 to 24. So see if you can answer both parts. What did your calculation part C represent? And go ahead and find the range over this domain. So do that now, please. Alright, how'd you do? Well, let me see. There it is. I knew it was in here somewhere. Alright, so first part, this calculation tells us the population at the end of 1 day, because remember we put in 24 for the time, which would be 24 hours or 1 day. So it grew 113 flies in 1 day. And then here is for the range. What you should have done is put in 0. We know it started at 28. And when we put in 24, it went to 113. So that's our range there, or you could wrote it like this also. And then you could put P for population. So there's several different ways you could write that. Alright, part E, using your calculator, see if you could sketch the graph of this function. It gives you a domain. Now you should know which one are x, y's. I won't tell you. It's kind of obvious though. Here's your one value. Here's the other value. So that's for your windows. And remember that when you do these, this right here is your y. Oh, wrong pen. This here is your y. So really it's more like y equals the 28 and then the 1.06 right in. And then now you don't have a t. You could still write an x, it doesn't matter, as long as it's a variable. So this is kind of what you would put into the calculator. So do that now and give it a try and try to sketch the graph, see what you come up with. Okay, how'd you do? So hopefully you got a graph something like this. It doesn't have to be perfect, obviously. Now what you could do is think about, obviously these were the x values. It says t right here, so this is 0. I'd kind of put 24 here. I should put it down. And then you can kind of just sketch, okay, in the middle is about obviously 12. The middle of that is 6. The middle of that is 9. It kind of gives you a way to figure out where those are. On here we went from 0 to 120. So again, I'd kind of 120. I'd kind of find the middle and say obviously that's 60. And then in the middle of that is about 30. So I would have actually brought that up a little higher. Not a big deal. And this is 90 here. Now the big thing when you do these exponential curves is notice that they gradually grow just a little. This is not ever straight. That means it would not be growing. It is growing. It's just growing slowly in the beginning. And then it starts to really increase as you go. So you'll get good at drawing this, but just kind of make it increase really slightly, and then it starts growing faster, and there you go. It's never going to be the exact same curve because it's growing more and more as you go. Okay? So get good at drawing those curves there. All right, here we go. So exponential growth is fairly easy to model and fairly easy to interpret in models. So we're going to consider the following examples here. And you should be able to easily answer exercise 2, so give that a try right now. Okay, so what did we find out? Well, you should know that this is the initial amount. So 250. We're not going to change it to, move decimals or anything. So obviously 250. And how much is it growing by? So remember, basically we move decimals twice when we're doing them. So if we go 1, 2, that's going to be 4.5 or 4.5%. So therefore we're looking for an initial amount of 250 and 4.5%. Not 45%. So the answer should be 3, hopefully. Okay, keep moving on. On this one, we're going to do basically the same thing, but we're going to look at decrease, or decay they call it. So you can see we have a water, it's draining out of a pool, so it's going down. The depth decreases at a constant rate of 20% per hour, and the depth is, when it starts beginning, it's at 12 feet. So right here, this is the same thing we've been doing as model example number 1. So we started at 12 feet. We are losing 20%, so therefore 80% is going to be the remainder. That's why we're multiplying it by the 80.8 right there. And then when you do that, you get 9.6. And then obviously we're going to keep doing, we have to multiply that by the 0.80. Remember, that's actually the 12 to 2 of them. And there we go. And now we're going to take this amount, which remember is this amount. We're going to multiply that by the 0.80, so really we have 3 of them, and there we go. So after 3 hours, we're down to about 6 feet, it looks like. So go ahead and write another model for that. See, again, you should be pretty good looking at this, how to write the model. Use the correct letters in your model. Okay, let's see if you got something like that. So the depth is based off time, so d of t, initial amount. The growth rate, this is actually a decay rate because it's less than 1. And there's your exponent t. All right, doing the exact same thing here is go ahead and sketch this. See if you can actually get a good growth curve. Now be careful, or decay curve, so be careful with that. So use it on your calculator and then try to sketch it again. Fill in some numbers on the graph so you can know where to put things. So do that now, please. All right, hopefully yours comes out looking like this. Okay, so again, we know that this was the x value, so it goes from 0 to about 20. So therefore, obviously, this is about 10. This is about 5. We got about 15 right there. And this one wanted us to go up to 15, so maybe 15's up here. 0's here. So half would be kind of hard because that'd be 7.5, so I might go a little lower, do something like 6. And then I could just do a couple more in here. Maybe 9, 3, something like that. And then as you can see, it's a decay, so it's going down at a slower rate, almost straight down, then it starts speeding up. And this again you should never make them straight. They're not going to be flat. They're always going down smaller, and they still are going down. They're just going down really slow at the end there. All right. Okay, so part D is safe to color the pool after it reaches a depth of 1 foot or less. What is the minimum number of whole hours that we should wait in order to cover the pool. So see if you could figure that out. So give that a try. Hit pause and give that one a try. All right, what did you come up with? The correct answer is you should have waited 12 hours. Now, the way I did is I put this in my calculator. You should already have it in your calculator. And bring up the table. You guys should be good at that now. These are the input values, the output values. We wanted to know when the depth was 1 foot, so you just kind of scroll down. You can see at 11 hours, there's still a little more than a foot, so we couldn't put that cover on there. But on the 12th hour, you can see it drop down to below a foot. So then you would be able to go ahead and cover it based on this. So use that table function on your calculator to come up with these output values. Much easier than just plugging them all in. Okay, let's keep going. Exercise 4, again, you should easily be able to do this one. What do we have here? We have an equation that would model exponential quantity. It starts at 16 and decreases at a rate of 8% per hour. So go ahead and figure out which one of those would be. All right, how did you do? Hopefully you came up with that equation there. So we had our remaining percent would be 92%. Starting value, and remember the way to write 92% is like that. So I believe, what are we looking for? Option 1 was the correct answer. Okay, exercise 5. Again, I want you to do this on your own, so give it a try now. All right, how did you do? So hopefully you ended up with this answer here. We had this initial amount here. And this is your percent when you move the decimal twice. 1, 2. And then when you add those, we didn't really show you this middle step here. You guys are just doing that on your own. You don't really have to write that. If you jump straight to here, that's fine. And then you plug in the 10 for the years that we wanted and came up with that 493.71. There we go. And I think that is it. Awesome. So we'll see you in class, and hopefully that went well.